Greetings, welcome to lecture number 33 on basic circuit theory. I am Razavi. Today we will switch gears to another type of RLC circuit, which we call the series RLC topology. And we'll take a qualitative look at the circuit and try to understand how it operates when it starts with an initial condition. And then we will try to find its natural response, meaning the response to an initial condition. But before we go there, let's review what we learned last time about the parallel RLC circuit with an input. We saw that, for example, if the input is a step, then in response to the step, we will have a current that flows through these devices, and that current will change with time. So we wrote the equations as follows. We said that the output voltage at time 0 plus has to be 0, because this capacitor doesn't want to change the voltage. And the inductor current also has to be 0. And from here, we found this equation in terms of V out. So then we wrote the differential equation for V out, and from there we decided that it's a second order system, so its response should be something of this nature, depending on what type of response we have. So we saw that in the case of an overdamped response, we have only these two terms, and we just require that the value of V out at 0 plus be 0. That gives us one equation here. And then we also would like the derivative to satisfy I1 over C1, and that gives us another equation here. Similarly, when we have a critically damped response, where we have a T here, and we have the two roots equal, then we end up with A1 being 0 from this condition, and A1 S1 plus A2 equal to I1 C over C1 from this condition. And finally, if we have an underdamped response, meaning that this resistor is large enough, then we have this equation, the third type of response, and then we have to go and satisfy both of these, which I didn't bother with here. So generally what we saw was that the output voltage as a function of time starts from 0, as we saw, and eventually also goes to 0, because at time infinity, this inductor acts as a short circuit and brings back the voltage to 0. Now, how it goes from 0 to 0 depends on the type of response that we have. If we have, for example, an overdamped response, it's going to go like this and gradually come back to 0. If we have a critically damped response, it goes faster and settles faster, optimally. And then if we have an underdamped response, it will go and ring for a while before it settles. So depending on the application, we might opt for a critically damped response or an oscillatory response, as we talked about it last time. Okay, so we might expect that similar results apply to a series RLC circuit. But of course, we have to analyze it and see if there are any differences between the parallel topology and the series topology, for example, in terms of the natural response. So let's go ahead and look at this in small steps. So series RLC circuit. Now, the first time we observed and arrived at a simple LC circuit, we placed one inductor and one capacitor in parallel. So naturally here we might expect that we should put one inductor and one capacitor in series, place some charge on the capacitor and let go and see what the circuit does. So let's do that. So I have a capacitor here and I have an inductor here in series, and that's all I have, right? So that closes the loop. And I have an initial condition V0 across this capacitor. And then I let go. I would like to see what the circuit does. Well, but is this a new circuit? No, this is the same as the parallel LC circuit we studied before. It's just drawn differently, right? So if you just rotate things, you will see that this circuit is the same as this circuit, right? So that's just this. So in this special case, the two devices are both in series and in parallel. Any two devices that are connected like this satisfy that condition. So we don't gain any additional information by analyzing the circuit because this is the same as what we saw before. All right? But to make the situation more realistic, we want to add some resistance to model the losses that we have, as we saw before. So let's go ahead and add a series resistor to this combination. So we won't bother with this topology anymore. And the circuit of interest to us will be something like this. I have a series resistor R1, then I have an inductor L1, okay? And then I have a capacitor, and they're all in series. So I just write like this because it's a little easier to write things into the circuit if it's in this form. You can see that they're all in series because they carry the same current. You see the current flows through all of them by the same amount. Okay, so this is the circuit of interest to us. Again, we have an initial condition of V0 on the capacitor and no initial condition through the inductor. Of course, in the general case, we should also include an initial condition here. Okay, so we want to release the circuit with this voltage across the capacitor and then see what happens to it. What happens to the different voltages and the current that flows through this loop. So let's, for example, look at the current. So let's say there's a current flowing through this loop. We expect that this capacitor is charged, and now this resistor and this inductor are drawing charge from the capacitor. They discharge in the capacitor over time. So we expect that the current will flow in this direction. We'll call that I1, right? And gradually discharges the capacitor. Okay, so let's just qualitatively predict how this current should change as a function of time. All right? Okay, so we're going to do this and see what we can predict about the behavior of the current. All right, well, how much is I1 at time 0 plus? It has to be 0 because the inductor wants to keep that current 0, right? So we know that the inductor current at 0 plus is 0, right? For this not to happen, we would need some infinite voltage coming to the inductor, and we just don't have an infinite voltage available here, so it has to be 0. So, and the current through the inductor happens to be the same current as that flowing through the rest of the circuit, I1. So I1 has to start from 0. Okay, and how much is I1 at time infinity? At time infinity it's also 0 because the energy in this capacitor is gradually lost to this resistor and everything dies away. So at time infinity we don't have any voltage left, any current left. So what we expect is that I1 at time infinity is also 0. So we're going from 0 to 0, and then in between we're doing something, right? So there's some peaking behavior. Okay, so that's what we expect the current to do. How about, of course, the current could have some ringing before it settles. Again, here I'm sort of assuming that I have an overdamped response or a critically damped response. But just generally speaking, we start from 0, we go to 0, and then in between, we will do something to get there. But another interesting observation here is the voltage across the inductor. So let's call that V out and try to sketch V out as a function of time. So what does that look like? So here's V out as a function of time. Okay, so we have to decide how much V out is at time 0 plus, how much V out is at time infinity, and then try to connect the dots, so to speak. Okay, so how much is V out at time 0 plus? What can we say about that? All right, so let's go back to the circuit and analyze it at time 0 plus. We still have a voltage of V0 across the cap. That voltage cannot change suddenly. We have no current through this loop because we saw that the inductor dictates that. So if the current through the loop is 0, the current through R1 is 0. If the current through R1 is 0, how much is the voltage drop across R1? That's also 0. So I will mark that by this color here. I will write this voltage is 0 volts. Right? The voltage from the left side of R1 to the right side of R1 is 0 because the current through it is 0 at time 0 plus. Okay? So now if this voltage is V0, how much is this voltage? These two have a difference of 0 because this guy has 0 drop on it, right? So whatever we have here has to appear here. So at time 0 plus, V out is actually equal to V0. That's interesting, right? So it starts at V0 here. All right? So you see we are following a logical thought sequence based on all the fundamentals that we are sure about. If I had tried to figure out this voltage at time 0 plus based on this inductor only, it would not have been easy, right? Okay, how much is the voltage here? I don't know. L1 is what is it doing? Is it open circuit? What is it, right? But by utilizing this resistor and finding the voltage on it, and then deciding that this voltage and this voltage have to differ by only this much, we can see that V out is equal to V0. All right, then what happens? Okay, so as time goes by, V out has to go to 0, right? Because we know at time infinity, all of the quantities have reached a constant value, and 0, of course. So if the voltage on the inductor has reached a constant value, the inductor has, or the current inductor has reached a constant value here, and then the voltage across the inductor is 0, right? So the voltage at infinity is 0, somewhere around here. So can I say that it goes like this? Let's assume it's an overdamped response, right? Can I say it goes like this? Not quite. Why not? Well, how much is V out in terms of I1? V out, the current going through the inductor, right? So it's just L1 dI1 over dt. Right? So then when I look at V out has to be proportional to the derivative of the current. Is that true? We can see that's not true. The derivative is positive here, so that's fine. The derivative is 0 here, so that's not fine. The derivative is negative here, so that's not fine. So that is not correct. So intuitively speaking, what we should see, I'll change the color again just to make sure it's clear. So we start from V0. At this point in time, because the derivative of the current is 0, V out has to be 0. So V out has to cross 0 here. Then it has to go negative because the derivative is negative. So we go negative, but eventually it comes back to 0. All right, so that is the correct response, not this one. All right, assuming that for now it's all overdamped, right? So if it's not overdamped, if it's underdamped, we expect that this will ring for a while, and this will also ring for a while before it settles, right? But in the case of overdamped, we expect this to be true. Okay, so that's the simple qualitative study of what the circuit will be doing in terms of this current and this voltage. The voltage across the cap is also interesting as a function of time, but we'll get to that a little later. All right, so now with these, we can go ahead and try to analyze the circuit carefully and to write equations for it and see what happens. So let's do that. So we'll say quantitative. So quantitative analysis. So here we are assuming that we have a voltage on the cap, we let the circuit go, and we are interested in the natural response of the circuit. So in other words, trying to find equations for these waveforms. Okay, so first I need to write the differential equation, right? So let's go ahead and see how we can arrive at that equation. We start with I1. I1 is the quantity first that we want to find. Why? It's a little easier. You could say, no, first I want to find V out, and that's okay too. You could find V out. You could find the differential equation for V out. But in this case, it's a little easier to find differential equation for I1, solve for I1, and then if we want to find V out, we have this equation, so it's easy, right? Okay, so how do we find V out? How do we find I1? So we say the voltage across the inductor is equal to L1 dI1 over dt. So let's write that voltage here. So L1 dI1 over dt. That's this voltage drop from here to here. How much is the voltage drop from here to here? And general time is I1 times R1. So I have I1 R1. And how much is the voltage across the cap? Well, if I have the current through the cap, which is called I1, I can find its voltage, right? So this current is going this way. You can see, right? So I can say the voltage on the cap, so I'm going to write that here. The voltage on the cap is 1 over the capacitance, integral of the current through it, I1 dt, except that the current is flowing from low potential to high potential, right? If I think of the voltage on the cap as this type of voltage in my mind, high potential is up here, low potential is here, then I can say this voltage is equal to 1 over C1 integral of this current, but with a negative sign because the current is going from low potential to high potential. Okay, so we have these three voltages, and we can write a KVL, and they all have to add up to 0 or something. We have to be careful how this is done, but we can do that, right? Okay, so how do we do that? Well, we say this voltage has this type of polarity, and I'm going up the potential, so I say plus here. And, sorry, there's a negative sign I have to include. Let's put the negative sign here first. Okay. All right, so that's the voltage across the capacitor, this is the voltage across the resistor, and this is the voltage across the inductor. We just have to carefully write a KVL for this whole thing. So what I could say is this voltage is equal to this voltage plus this voltage, right? So I can say this voltage is equal to the sum of these two. So now we bring everything to one side, and we take the derivative with respect to time so as to obtain a second order differential equation. So I'll write that up here. So you can see that this gives us the second derivative. So L1 d squared I1 over dt squared plus this gives us the first derivative, R1 di1 over dt. And finally, this gives us just the, comes to this side, it gets a positive sign. 1 over C1 I is equal to 0. All right, so that's our differential equation. Subject to two initial conditions, always, right? It's the second order. So initial conditions are what? So I1 is equal to 0 at 0 plus. So that's one thing we know. Why? Because the inductor started out with the 0 initial condition, so that has to be satisfied. We know also one more condition. The condition is that the voltage on the cap at time 0 plus is V0. So we say V cap at 0 plus is equal to V0. All right, so now we have to solve this equation subject to these initial conditions and find the response. All right, so as usual, we write the characteristic equation first. The characteristic equation will be like so. So it's L1 S squared plus R1 S plus 1 over C1 equals 0. Is that right? Okay, so we can even try to write it in this form, which is a little easier to see. So we'll say divide by L1. So we have R1 over L1 times S plus 1 over L1 C1 equals 0. All right. So again, we have two roots, and depending on what the roots are doing, we have one of these three responses, right? If the roots are real and unequal, we have an overdamped response. If the roots are real and equal, then we have this critically damped response. And if the roots are complex, we have this sinusoidal response with a decaying exponential envelope. All right, so, but let's just write the two roots, S12. That would be minus R1 over 2L1, because remember 2A is 2, and then plus minus R1 squared over L1 squared minus 4 over L1 C1. All right? So that's the equation that we have for the two roots of this equation. What's the unit of S? Remember we said that the unit of S has to be 1 over time. The dimension has to be 1 over time because it's the part of an exponent and it's multiplied by t. The exponent cannot have a unit, so it has to be, S has to have a unit of 1 over time, a dimension of 1 over time. And this checks out, at least for this term, right? This has a dimension of 1 over time. How do we know that? Well, remember that the time constant we found in RL circuits was of the form tau equals L over R. So L over R has the dimension of time. So R over L has the dimension of 1 over time. So that makes sense. Okay, so we are interested to know how this term under the square root becomes positive, 0, or negative. So, and that tells us what's going on, right? Which one of these solutions we have to select. So we have R1 squared over L1 squared, and whether it's greater than 0 or less than 0, right? Or rather, whether this whole thing is greater than 0, 0 or less than 0, which corresponds to these three conditions. So if you simplify this, we get something like that. So we get R1. So I'm going to do this very carefully, okay? So R1 is greater than 1/2 of L1C1 or equal or less. Does this look like what we got for the parallel RLC circuit? Yes and no. So we have to be very careful here. For the parallel RLC circuit, we said if R1 is small enough, we have an overdamped response. Here, if R1 is large enough, we have an overdamped response. So it's the opposite. It's the opposite direction. So if R1 is large, the circuit has an overdamped response. It doesn't ring. If R1 is small, the circuit has an underdamped response and it rings. Okay? So I want to make sure that the series and the parallel RLC circuits are not confused in terms of this behavior. So then we say if, I'll write it here, if R1 is large enough, we have an overdamped response. Okay, large enough meaning R1 is greater than 1/2 of root L1 over C1, then this guarantees that this root is positive, and this term is positive, so the roots are real and unequal. Okay, all right, so we're gradually making our way towards writing these solutions, and to figure out which solution is the proper solution, we have to understand whether this term is positive, 0, or negative, right? And that translates to these conditions. R1 greater than this value, or equal to this value, or less than this value. All right, so now the situation is reverse of what we saw for the parallel RLC circuit. And is there any intuition to explain why this is true? So if I compare the parallel RLC circuit and the series RLC circuit, the conditions are opposite of each other for underdamped versus overdamped. So I want to understand why that is true. So let's just make a quick comparison here, and that will show us why. So comparison of parallel and series RLC circuits. This is a brief comparison for now. Later on we'll make a more detailed comparison. I just wanted to show you intuitively why the condition is reversed. All right, we started with what we know. So remember, we have a cap, an inductor, and a resistor in the parallel combination. We start out with V0 and let go, right? And what we saw is that as this resistor becomes smaller, and the response does not ring as much, and eventually it just doesn't ring. It just settles, right? Why is that? Well, because we saw that in the extreme case, if R1 is infinity, the circuit reduces to an ideal LC tank, which will ring forever, which will oscillate forever, right? So we saw that if R1 is infinity, oscillates. The circuit oscillates, right? So we start from that point. We say, okay, now if R1 is not infinity, anything less than infinity, it will not oscillate, it will just oscillate and decay. And if R1 becomes smaller and smaller, that decay becomes faster, and eventually we don't have any oscillation. All right, so the starting point is when R1 is infinity, so that the circuit reduces to something that we know and we intuitively understand. Now let's go and look at the series combination. So here's the series combination. I have C1 starting with initial condition V0, then I have R1, and then I have L1. So this time I'm going to start with R1 equals 0 and see what happens. R1 equals 0. So the capacitor has an initial voltage, and R1 can have some value. I pick it to be 0. What happens? Well, if R1 is 0, this circuit just reduces to this circuit, right? It's just simple parallel series LC circuit, and it will oscillate indefinitely. So we say oscillates forever. All right? So it's important to understand that if this R1, this parallel resistance is infinite, and if this series resistance is 0, these two circuits are one and the same. They're identical, right? And of course, they both oscillate. But now, if R1 is not 0, if it's some larger amount, it begins to dampen that oscillation, right? It begins to kill that oscillation. As R1 becomes larger and larger, we kill the oscillation more, and if R1 is large enough, then the oscillation does not occur. So that's the distinction. So here we say R1 equals R1 greater than 1/2 of L1 over C1 dampens the oscillation. Right? So if R1 is large enough, we have something like this. There's no ringing in the response. On the other hand, here we decided that if R1 is less than that value, then that dampens the oscillation. Okay? So anytime in doubt, for these two circuits, you go to one extreme case. This time, for this one, the extreme case is when the resistance is infinity. The circuit is now known, familiar. And here, the extreme case is when R1 is 0. Again, the circuit is known and familiar. Based on that, we can determine what happens is if R1 is not infinite or not 0 in between. All right? Okay, so let's continue with our analysis. And again, based on the value of R1 with respect to this value, we can decide what type of response we should expect. So we're going to just write all these three here, so nothing really to it. But what we need to find are these coefficients. All right? Okay. So let's go ahead and decide what else we can do here. All right. Okay. So I need to manipulate this condition so that I can find an equivalent condition in terms of I1. Remember, our final equation is something like this for I1. I don't have an equation for V out yet, or for V cap yet, right? So I have to recast this in a language, in a form that has only I1 in it. So what can I say about that? Maybe I'll try to squeeze that here and see. Okay, so what we know is that the capacitor voltage is V0, right? Okay, so we say V cap at 0 plus is V0. And of course, that doesn't depend on the type of response we have. It's always V0 at time 0 plus, regardless of the values that we have for the resistors, the resistor and the inductor and the capacitor. Okay, so how can I convert this to something that only has I1 in it? Okay, well, what I can say is that if this voltage is V0, how much is the voltage across the inductor at time 0 plus? We decided that was also V0, right? So we say that V inductor at 0 plus is also V0. Remember, that's what we found here. We called it V out or V inductor. Is that okay? All right. Now, if that's the case, I also know something. I know that the inductor voltage is equal to L1 di1 over dt. So I can say L1 di1 over dt at time 0 plus has to be equal to V0. Is that okay? So that means that di1 over dt at time 0 plus has to be equal to V0 over L1. So at time 0 plus has to be equal to V0 over L1. All right, so we're going to remember this. So now we have both of our initial conditions in terms of I1, right? So we know I1 itself has to be 0 at 0 plus, and we know that the derivative of I1 at 0 plus has to be V0 over L1. These are somewhat similar to what we found before for the parallel circuit. Remember that here we said we have this voltage to be 0 at 0 plus, so that's good in terms of V out. And then we had the current of the inductor to be 0, and we wanted to change it to a form that has V out in it, so we end up with this equation. So we said dV out over dt at 0 plus is I1 over C1. Now here we see that di1 over dt at 0 plus is V0 over L1. All right, so we have these. So based on this equation, and the value of R1, it compares with this value, we can go ahead and select one of these three responses. So let's go to the next page and see what we can do. Okay, so we say three natural responses. So one, if R1 is large enough, we have an overdamped response. So overdamped, and what we have is I1 of t, the current that flows through the entire loop, is given by a1 e to the s1t plus a2 e to the s2t. S1 and S2 are found as I showed you before on the previous page. Okay, so we have to find A1 and A2. But before we do that, does this take U of t? Yes, because it's 0 before times 0, right? So why don't we just multiply that by U of t so that we have that. Okay, so to find A1 and A2, we say I1 at 0 plus 0. That means A1 plus A2 is equal to 0. All right. Okay, what else? We also know that the derivative of I1 with respect to time at 0 plus is given by V0 over L1, as we calculated down here on the previous page. So we say the derivative of I1 over with respect to time at 0 plus is equal to V0 over L1. And how much is that? Well, let's take the derivative of this. So we have A1 S1 plus A2 S2, because I'm evaluating it at time 0. Again, you can always ask, okay, so the derivative of this times this, that's great. How about the derivative of this times this? That would be an impulse. And that impulse has an area or a weight equal to this calculated at time 0. How much is this at time 0? This whole thing. 0, right? Because that's what it is. So, because it comes from this condition. So that's why we don't worry about that impulse. That impulse has an area of 0, so it goes out of the picture. Okay, so from these two equations, we can find A1 and A2. And now we have the complete solution. All right, how about the other case? The next case is if we have equal roots for the characteristic equation, and that means that we have a critically damped response, and that means that I1 of t is equal to A1 e to the s1t plus a2t e to the s1t. And again, this takes a u of t, right? Because it's 0 before time 0. All right. Okay, and now we go ahead and try to satisfy this condition and this condition. So at time 0, we have a1 is equal to 0, so that goes away. We have only this term left. And then the derivative, meaning a1 s1, derivative of this, plus the derivative of t1 times that, plus a2 is equal to v0 over L1. All right, so I should satisfy this condition and this condition. I got these two. So I can find A2, we're done. And finally, we have the case of underdamped response. So R1 is small enough, the circuit rings L1 over C1. So this is underdamped. And the result will be of this form. I1 of t is equal to A1 e to the alpha t cosine of omega 1t plus A2 e to the alpha t sine of omega 1t, and then again u of t. All right, how much are alpha and omega 1? Well, if you write the characteristic equation, we remember that, right? So remember that we said the roots are given by this, S1 and 2. It was something like minus R1 over L2L1 plus minus 1 over 2 R1 over L1, R1 squared over L1 squared minus 4 over L1 C1. Did I forget this factor 1/2 on the previous slide? let's go back and make sure it is there. So yes, there's a factor of 1/2 here that I forgot. So these are the two roots, right, given by this equation. And so that's what I wrote on the next slide. So let's go here. And this is what we have. Okay. All right. So I'm going to write this in the following form. If this condition is true, so I will write it as R1 over 2L1, then plus minus 1/2 J, and I swap these two. So now I have square root of 4 over L1 C1 minus R1 squared over L1 squared. So now I can see that this alpha, which determines how fast this exponential decays, is given by the first term. So this is alpha. And then omega 1, which is sort of the frequency of that ringing, is given by all of this here. So that's omega 1. Okay? So we have those. So we still need to find A1 and A2. Not a problem. Same story as before, right? So we have to satisfy this condition. We have to satisfy this condition. So we say A1 at time 0. This is 0. So this is A1. So A1 is equal to 0. So again, this goes away. We have only a sine, not a cosine. And then we have to take the derivative of this and satisfy it by equating to V0 over L1. So again, that's something you can do on your own. So we'll just write di1 over dt evaluated at 0 plus has to be equal to V0 over L1. So we take the derivative of this function at time 0 and calculate it at time 0 plus equate to V0 over L1. That gives us A2. And now we have the complete solution. Okay, so this was a quick analysis of the series RLC circuit. We see that the responses agree with what we would expect of a second-order system, right? A second-order system is governed by a second-order differential equation, so it must have these three possibilities, right? An overdamped response if the resistance is large enough, a critically damped response if the resistance is equal to this value, and an underdamped response if the resistance is small enough, right? As the resistance becomes smaller and smaller, the series of the capacitor and the resistor and the inductor approaches an ideal LC tank. So an ideal LC tank will just oscillate forever. And that happens if R1 is very, very small, right? 0, that is. Okay, so that is what we get for the natural response of the circuit. Now, there are some other interesting things that we can ask. In particular, if I go back to the previous slide here, I have found I1. Can I find V out? Sure, it's just the derivative of those three expressions that we have multiplied by L1. So that's not that hard, right? We can always do that. And of course, our intuition said that, for example, for the overdamped case, V out should have a dip below 0, right? It cannot just go like this. So it should have a dip, so it's not exactly monotonic, but only one dip. As we go to a critically damped response, this settles faster, and this also settles faster to 0, but still has a dip. And then as we go to an underdamped response, when this resistance is really small, then this will ring before it settles, and this voltage will also ring before it settles. All right, so that's easy. But one more parameter of interest to us is the voltage across this capacitor. And we'd like to calculate that based on what we've done here, or independently, right, as a function of time. So again, that voltage should satisfy one of these three cases, three responses. Of course, if, for example, the current through the network has an overdamped response, then everything in the network has an overdamped response, right? Because they're all dictated by this type of relationship, which is independent of the initial condition on the circuit or the current and the voltages, right? So these are just properties of the circuit when we build it. But the calculation of the capacitor voltage as a function of time is a little tricky. And I will keep you in suspense, and I'll look at that next time. I'll see you next time.